Welcome to Lecture 3. This week I'm going to talk about polar coordinates, conic sections, and three-dimensional Cartesian coordinates. First, polar coordinates. We could describe the position of a point in the plane using Cartesian coordinates, x position and y position, but it's not the only way to describe the position of a point. We could also describe the position of the point by giving the distance from the point to the origin. We call that distance r, and then by measuring the angle from the x-axis to the ray between the origin and P, and we call this angle theta. Now, when we're measuring this angle, if we measure in an anti-clockwise direction, then we say that the angle is a positive angle. If we measure it clockwise, then we say we have a negative angle. You can think of polar coordinates like this. Let's suppose we have a ruler, which to start with, we put 0 on the ruler at the origin, and we have the ruler along the x-axis. Now, this is a special mathematical ruler because this has negative numbers on as well as positive numbers. And then let's suppose we rotate the angle. We rotate the ruler by an angle of 45 degrees in the anti-clockwise direction, so plus 45 degrees. And then we can measure the polar coordinates along the ruler. For example, this is the point with polar coordinates 1, 45 degrees, because the distance from this point to the origin is 1, and the angle the ruler makes is 45 degrees. Or this one is the point with polar coordinates 3, 45 degrees. And here's a point with polar coordinates 4.5, 45 degrees. We could also go to negative numbers. This is the point which has polar coordinates -2, 45 degrees. Let's put the ruler back on the x-axis. This time I'm going to rotate the angle clockwise, so we'll have a negative angle. I've rotated the ruler by an angle of -30 degrees, and then we can measure along the polar coordinates. So for example, this is the point which has polar coordinates 4, -30 degrees. Now, polar coordinates are not unique. Let's suppose I want to find the polar coordinates of the point P here. The distance from the point P to the origin 2, and this angle is 30 degrees. So this point P has polar coordinates 2, 30 degrees. But there's another angle here we could use. Instead of going anti-clockwise, we can go clockwise for an angle of 330 degrees. This point P also has polar coordinates 2, -330 degrees. Or if I wanted to, I could go anti-clockwise, but I could go all of the way around the circle and then another 30 degrees. So that would be the angle of 390 degrees, 360 plus 30. The point has coordinates 2, 390 degrees as well. This point also has distance from the point to the origin 2, and the red angle I've drawn here is 210 degrees. So the polar coordinates of this point are 2, 210 degrees. Or if we wanted to, we could use negative distance. We could say the distance is -2 if the angle is 30. Now, you'll notice that the difference between these two angles is 180 degrees because they point in different directions. For example, find all of the polar coordinates of 30 degrees. The first thing to say is that we have a choice of two distances. We could either have the distance r equal to 2 or the distance r equal to -2. First, let's look at r equal to 2. We've seen that the angle is 30 degrees, or we could add on 360 to get 390. We could have 30 plus 360 degrees. Or we could subtract 360 degrees to get minus 330 degrees. We've done that already as well. Or if we wanted to, we can go around 2 times, 30 plus or minus 720 degrees. Or we can go all the way around 3 times, 1080 degrees, and then plus our 30, or 30 minus 1080, etc. If we're using minus 2, we've seen that one of the angles which works is 210 degrees. But then, of course, we can add on 360, add on 720, add on 1080, etc. Or we could subtract these angles as well. So the polar coordinates of the point 230 are 2, 30 plus any multiple of 360 degrees, or minus 2, 210 plus any multiple of 360. Draw the graph r equal to a. R is the distance from the origin and a is a constant. If the distance from the origin to a graph is always the same, then we end up with a circle. And it's a circle of radius absolute value of a. If a is a positive number, we have a radius of a. If a is a negative number, then we have a radius of minus a. Draw the graph theta equal to b. All of the points which have angle equal to b. That's a straight line passing through the origin. Now, r equal to 1 and r equal to minus 1 are both equations for the same circle. It's a circle of radius 1. Theta equal to 30 degrees, theta equal to 210 degrees, theta equal to minus 150 degrees, etc. The difference between these angles is 180 degrees each time. These are all equations for the same line. For example, draw the set of points whose polar coordinates satisfy the following 2 conditions. R is between 1 and 2, theta is between 0 and 90 degrees. Let's look at these 4 conditions separately. First, we have r equal to 1. That's a circle of radius 1. Our next condition is r is equal to 2. That's a circle of radius 2. Move on to the second equation. Theta equal to 0. That's easy. And then theta equal to 90 degrees. Again, straight up. We want the region which is between these 4 lines. So we want this region, which I'm colouring in blue. Let's tidy this up a little bit. The answer is this blue region. Draw the set of points whose polar coordinates satisfy the following. R is between minus 3 and 2. Theta is equal to 45 degrees. Let's start with the second equation this time. Theta equal to 45 degrees. We can draw that. That's a line passing through the origin with an angle of 45 degrees. And then R is between minus 3 and 2. 2 is about here. 3 is about here. So we want the part of the orange line which is between these 2 points. Draw the set of points whose polar coordinates satisfy. R is strictly less than, R is less than or equal to 0 and theta is equal to 60 degrees. Again, let's look at the angle. Theta equal to 60 degrees, that's about here. But we just want the negative part of the line. So we just want this part down here. And finally, draw the set of points whose polar coordinates satisfy that theta is between 120 degrees and 150 degrees. So 120 degrees, start at X, rotate anti-clockwise, 90 degrees, point straight up, do another 30 degrees, and we get to about here. And 150 degrees, rotate another 30 degrees, we get to about here. We want the center points which are between these two lines. We want to draw this region. We can relate polar and Cartesian coordinates using this picture. Look at this triangle here. Using trigonometry, x is the same as r cos theta, y is the same as r sine theta. So by Pythagoras, x squared plus y squared must be r squared. And then rearranging these, we get that tan theta is y over x. So for example, convert the polar coordinates r theta equal to -3, 90 degrees into Cartesian coordinates. The question tells us r and theta, and it asks us to calculate x and y. So I'm going to start with the formulae. X is r cos theta and y is r sine theta. And then it's just a case of putting the numbers in, -3 cos 90 and -3 sine 90, and then calculating them to get 0 minus 3. Find polar coordinates for the Cartesian coordinates. xy is equal to 5 minus 12. This time we're told x and y, and we want to find r and theta. There are infinitely many correct answers to this question. We just need to find one correct answer. The first thing to do is to decide, do we want r to be a positive number or do we want r to be a negative number? I'm going to choose to have r a positive number. And then I'm using the formula r squared is equal to x squared plus y squared, or r is the square root of x squared plus y squared. Put the numbers in and I find that r is 13. Next, I need to find an angle. And to find the angle, I'm going to use the formula y is equal to r sine theta. Using this, rearranging it to theta is inverse sine of y over x, I get approximately minus 67.38. So the one answer to this question is 13, minus 67.38 degrees. Now, it's easy to make a mistake when we measure this angle, so it's always a good idea to draw a picture and just see if this answer looks correct. This is the point P with x coordinate 5, y coordinate minus 12. Does the distance look like 13? Yes, that looks about right. And does the angle look at roughly minus 67? Yes. So it looks like our answer is correct. Next, I want to talk about conic sections. Let's imagine we have a double cone, a hollow double cone, and I want to imagine that we're cutting this cone in different ways. First, I want to cut the cone horizontally, or to say it another way, I want to take a horizontal green plane, and I want to look at the intersection between my green plane and my blue double cone. This one's straightforward. The intersection is just a circle, and we know a formula for a circle. Next, suppose that we slant our green plane a little bit. What is the intersection between the green plane and the blue cone? We have a shape which is called an ellipse. Let's make our green plane steeper still. And if I can quickly draw a three-dimensional picture, so a two-dimensional picture, suppose we're looking from the side. This is my double cone. I want to cut the cone in such a way that my cut is parallel to the edge of the cone. Then the shape that we get is a parabola. Next, let's make our cut even steeper so that it cuts the top half and it cuts the bottom half. Then we get a curve like this. This is called a hyperbola. First, let's talk about parabolas. Where do we see these? For example, in a bouncing ball, or on a suspension bridge. Now, actually, the cables in a suspension bridge hang in a shape which is almost but not exactly a parabola. Why is it not exactly a parabola? It's because of the forces of the bridge pulling down on the cable. If you become a bridge engineer, if you become a bridge architect, you can ask your engineers why it's not exactly a parabola. But if we want to draw a suspension bridge, usually we just draw a parabola. And we see parabolas on satellite dishes. I'll explain why later. To describe a parabola, we need a point called a focus, and we need a line called a directrix. Here's a picture. My focus is the point 0p, and my directrix is the line y is equal to minus p. And then I have a parabola in the middle. The rule is that a point on the parabola must satisfy the rule that the distance from the point P to the focus is the same as the distance from the point P to the line. That's the shortest distance from the point to the line, so the straight down. Formally, a point P lies on a parabola if and only if the distance from P to F is the same as the distance from P to Q. Now, the distance from P to F, we can measure this. It's the distance from the point xy to the point 0p. So it's square root of x minus 0 squared plus y minus p squared. The distance from P to Q is the distance between x and y and x and minus p. And we can calculate that that's y plus p. And these two distances must be the same if we have a parabola. So we must have that the square root of x squared plus y minus p squared is equal to y plus p. If we rearrange and simplify this, we end up with the standard equation for a parabola. X squared is equal to 4py. Let me just summarize. This is the graph of x squared is equal to 4py, or we could rearrange that to y is equal to x squared divided by 4p. The focus is the point 0p, and the directrix is the line y is equal to minus p. We could flip this picture upside down just by multiplying by minus 1. Now I have the equation x squared is minus 4py. The focus is 0 minus p. And instead of y is equal to minus p, now the directrix is y is equal to p. Or I might have a parabola which opens to the right. I can do that by taking the previous equation and swapping x and y. Instead of x squared is equal to 4py, I have y squared is equal to 4px. Then the focus is the point P0 and the directrix is the point x is equal to minus p. Or multiply by minus 1, we will get a parabola which opens to the left. Y squared is minus 4px with the focus minus P0 and the directrix x is equal to p. We can use these to answer questions like this. Find the focus and the directrix of the parabola y squared is equal to 10x. Now, our formula, y squared is equal to 10x, looks like y squared is equal to 4px, but where p is 10 divided by 4, or 2.5. So it looks like we have a parabola like this, which opens to the right. Then we can read off that the focus is the point P0, that's 2.50, and the directrix is the line x is equal to minus b, x is equal to minus 2.5. Or we can go the other way. Find the equation for the parabola which has focus at 0, minus 10, and directrix y is equal to 10. Now, clearly we can see P must be 10. And if we look at the previous 4 pictures, we see that we must have a parabola of the form x squared is equal to minus 4py. So the answer to this question is x squared is minus 40y. Next, let's talk about ellipses. We can draw an ellipse by taking a bit of string, fixing it in its two ends to a bit of paper, and then drawing around using a pencil. Where do we see ellipses? The orbits of planets in our solar system, for example, are ellipses, or we often see them in architecture, for example, this building in Denmark. To describe the ellipse, we need two foci. Let's suppose we have the foci minus C0 and C0. And then the rule for an ellipse, and this is the same idea as drawing an ellipse using a bit of string which is attached at its endpoints to a bit of paper. The rule is that the distance from P to F1 plus the distance from P to F2 is always a constant. And I'm going to call the constant 2a. So formally, a point P is on an ellipse if and only if the distance from P to F1 plus the distance from P to F2 is equal to the constant 2a. So in terms of coordinates, that's the same as saying that the square root of x plus c squared plus y squared plus square root of x minus c squared plus y squared is equal to 2a. And I'll leave it for you to check that this can be rearranged to x squared over a squared plus y squared over a squared minus c squared is equal to 1. At this point, I want to introduce a new number. I want to introduce b is equal to the square root of a squared minus c squared. And then we have the standard form, x squared over a squared plus y squared over b squared is equal to 1. Now note, because of the way that b is defined, b is the square root of a squared minus c squared, b must be a positive number and b must be smaller than a. So let's summarize this with a picture. This is the ellipse. X squared over a squared plus y squared over b squared is equal to 1, where 0 is less than b is less than a. Now note, if y is equal to 0, we just get x squared over a squared is equal to 1. So that's y is equal to a and y is equal to minus a. So x is a, x is minus a. Or if we say let's put x equal to 0, then we get y squared over b squared is equal to 1. So y is equal to b or y is equal to minus b. C is the center to focus distance. And because of the way that we define b, if we go back to the previous slide and then rearrange that, c is the square root of a squared minus b squared. Because a is a bigger number than b, that's okay. We're not going to be taking the square root of a negative number. The foci is the plural of focus. The foci at minus c0 and at c0. And the vertices are at minus a0 and a0. This is an ellipse with foci on the x-axis, but we might also have an ellipse with foci on the y-axis, and we can do that just by swapping x and y around. This is the ellipse x squared over b squared plus y squared over a squared is equal to 1. And again, I want to insist that the bigger number is called a and the smaller number is called b. Why? So that the center to focus distance stays the same. C is the square root of a squared minus b squared. No change there. The foci, we have one focus at 0 minus c, and we have another focus at 0 c. And the vertices are, these are the points where the ellipse intersects its longer axis. These are at 0 minus a and at 0 a. For example, the ellipse x squared over 16 plus y squared over 9 is equal to 1. The bigger number I want to call a, and the smaller number I want to call b. So a is 4 and b is 3. The center to focus distance is then the square root of 16 minus 9, or square root of 7. The center is at 0, 0. The foci are at minus c0 and c0. The vertices are at minus a0 and a0. Or the ellipse x squared over 16 plus y squared over 25 equal to 1 has bigger number needs to be a and the smaller number needs to be b. So a is 5 and b is 4. The center to focus distance we can calculate is 3. The center is at 0, 0, always at 0, 0. The foci are at 0 minus c and 0 c. The vertices are at 0 minus a and 0 a. Next, hyperbolas. Where do we see hyperbolas? For example, on cooling towers. These curves, which I'm going to draw on the edge of a cooling tower, are hyperbolas. Or, for example, this building in Japan is built using hyperbolas. For a hyperbola, again, we need two foci, and we need to measure the distance from our point P to each foci. But instead of adding these distances together, we want to take the difference between these two distances. The difference between the distance from P to F1 and the distance from P to F2. And because we don't know which one of these numbers is going to be bigger, we need to put absolute value signs around this. We need this to be a constant. And again, I'm going to call the constant 2a. So formally, to describe a parabola, we need two foci. Point P is on a hyperbola if and only if the absolute value of the distance from P to F1 minus the distance from P to F2 is equal to a constant, which I call 2a. In terms of coordinates, we have the first equation, and you can check by squaring this and rearranging this that this rearranges to x squared over a squared plus y squared over a squared minus c squared is equal to 1, where c is bigger than a. This time I'm going to replace square root of c squared minus a squared by a new number b. And then I have the standard form x squared over a squared minus y squared over b squared is equal to 1. So let's summarize. This is the hyperbola x squared over a squared minus y squared over b squared is equal to 1. Now, this time it doesn't matter which of the numbers a and b is bigger. The center to focus distance now is c is equal to the square root of a squared plus b squared. For an ellipse, we had a plus in the equation and we had a minus in the center to focus distance. Now we have a minus in the equation and a plus in the center to focus distance. Because we've got a plus in the center to focus distance, that's why it doesn't matter if A is bigger than B or B is bigger than A. And then the foci and the vertices are where we would expect them to be. The foci at minus C0 and at C0, the vertices are at minus A0 and A0. Multiply this by -1, or swap, sorry, let me say that again. Swap x and y, and we rotate our hyperbola by 90 degrees. This is y squared over a squared minus x squared over b squared is equal to 1. The center to focus distance is the same. The foci now are on the y-axis, so 0 minus c, 0, c, and the vertices are also on the y-axis, 0 minus a and 0, a. For example, the hyperbola x squared over 4 minus y squared over 5 is equal to 1. Here, a is 2 and b is the square root of 5. The center is at 0, 0. The center to focus distance, c is the square root of a squared plus b squared, is 3. So the foci are at minus 3, 0 and 3, 0, and the vertices are at minus a0 and a0, minus 2, 0 and 2, 0. Another hyperbola, y squared over 9 minus x squared over 16 is equal to 1. Here, a is 3 and b is 4. The center is 0, 0, and the center to focus distance is 5. Because y is the first variable in the equation, that means that the foci and the vertices must be on the y-axis. So the foci are at 0, minus 5 and 0, 5. The vertices are at 0, minus 3 and 0, 3. Now, why are we interested in conic sections? We're interested in them in architecture and engineering because of their reflective properties. First, parabola has the property that rays which originate at the focus are reflected by the parabola as parallel lines. If I start at the focus and I shine a bit of light or I make a bit of sound, this bounces off the parabola and goes this way. Take another one, bounces off the parabola and then goes straight up. And that's useful, for example, in car headlights. In a car headlight, we put a light at the focus of the parabola and then we put a mirror which is shaped like a parabola. Or it's useful on satellite dishes. What we do is we put the receiver at the focus. We have our satellite up in orbit, which is beaming our television signal down. The signal hits the parabolic dish and then it's reflected to the receiver. Or something in architecture, this is called a whispering dish. This one's in San Francisco and it's one of a pair. The other one is some long way over to the right. And the chair is built so that if you sit in this chair, your head is at the focus of this parabolic dish. And then over on the right, you have another chair and another person sitting with their head at the focus. And then one of the people sitting here talks, the sound of their voice hits the parabolic dish and is reflected across to the other one. And then the second parabolic dish reflects the sound to the head of this person. These two people can sit a long way apart, but they can talk to each other because their voices are reflected by the dishes. An ellipse has the property that rays which originate at one focus are reflected to the other focus. So for example, if two people are standing in a crowded room, but if they stand at the foci of the elliptic room, they can talk to each other because their voices are reflected or echoing off the walls of the building to the other person. And that's also true if we were in a subway tunnel which was shaped like an ellipse. Now, when architects understand this, they build elliptic rooms with these properties. This is perhaps the most famous elliptic room in the world. And the architects of this room knew their conic sections. A parabola also has reflective properties. It has the property that if rays, and this I've only drawn one half of the hyperbola here, rays which shine towards one focus of a hyperbola are reflected to the other one. Telescope manufacturers use these properties. This is a simple telescope which uses one parabolic mirror and one hyperbolic mirror. Now, the focus of the parabola is about here. And this is also one of the foci of the hyperbola. Light rays enter the telescope and they bounce off the parabolic mirror towards the focus of the parabola. They then hit the hyperbolic second mirror, and the hyperbolic second mirror reflects them towards its other focus. This is a simple telescope. More advanced telescopes would have more mirrors, but the idea is the same. You would use parabolic, elliptic, and hyperbolic mirrors to focus the beams of light. My third and final chapter for today's lesson is about three-dimensional Cartesian coordinates. To describe the position of a point in three-dimensional space, we need three numbers: an x-coordinate, a y-coordinate, and a z-coordinate. Now, when we draw three-dimensional coordinates, we need to use the left hand rule. Imagine holding your left hand up, like I've drawn in the picture here. This tells us the directions of the x, y, and z axes. Rotate our hand around so that your second finger points in the direction of the x-axis, your first finger points in the direction of the y-axis, and then your thumb will give the direction of the z-axis. Or there's another way to think about this. You could use your right hand, again using your thumb to point in the direction of the z-axis, and then your fingers point from the x-axis to the y-axis. Whichever one of these makes more sense to you. Use your left hand or use your right hand. In three-dimensional space, the equation x equal to 0, all of the coordinates where x is 0, y can be any number, z can be any number, is a plane which we call the yz plane. Y equal to 0 is the xz plane. X can be any number, z can be any number, but y must be 0. Z equal to 0 is this plane. Put them all together. They look like this. Now, we don't have to have equal to 0. We might have, say, y equal to 3, or the points where x can be any number, y must be 3, and z can be any number, and we have a plane z equal to 5. These two planes intersect in a line. It's the line where y is equal to 3 and z is equal to 5. Now, for example, let's talk about these equations. Z greater than or equal to 0. So x can be any number and y can be any number, but z must be greater than or equal to 0. That's half of three-dimensional space. It's the top half. It's everything which is on or above the xy plane. X equal to minus 3. That's a plane. It's a plane which is perpendicular to the x-axis and has x equal to minus 3. Z equal to 0, x less than or equal to 0, y greater than 0. Z equal to 0 tells us we're in the xy plane, and then if x is less than or equal to y is greater than 0, then we're in a quarter of the xy plane. And so on. Which points x, y, z satisfy x squared plus y squared is equal to 4 and z is equal to 3? Now, we know that z equal to 3 is a horizontal plane, and we know that x squared plus y squared equal to 4 is the equation of a circle. So we have a circle which is on the plane z equal to 3. We can measure distance in three-dimensional space. How do we write three-dimensional space? We write it as r cubed. Just as we were using r squared for two-dimensional space, we use r3 for three-dimensional space. So it's all of the points x, y, z, where each of x, y, z is a real number. So we've got 3 real numbers, or real number, real number, real number, so real number cubed. Just as we were doing in two-dimensional space, the distance from a point P1 and the point P2 is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So, for example, the distance between 215 and minus 230. Put these numbers into our formula, which I've got in the yellow box at the top. And we calculate that the answer is 3 square root of 5, which is roughly 6.7, but in an exam, I would expect you to give your answer as 3 square root of 5. Let's talk briefly about spheres. A point P lies on the surface of a sphere with center at P0 if the equation distance from P0 to P is equal to a constant A is satisfied. Now, because we have our formula for distance, we can write down the standard form. The standard equation for sphere of radius A, centered at the point x0, y0, z0 is x minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to a squared. For example, find the center and radius of the sphere x squared plus y squared plus z squared plus 3x minus 4z plus 1 is equal to 0. Now that doesn't look like the standard equation which I've written in the top. So the first thing we need to do is that we need to rearrange our equation so that it is in the standard form. And what we're going to be doing is we're going to be completing the squares here. We're going to be using the fact that x minus b squared is x squared minus 2b plus b squared. Now note that the number inside the bracket, the b, is always a half of the number. Oh, there's a typo here, of course. There should be an x just here. It's half of the coefficient of x. Okay, so first let's group together all of the x terms, the y terms, and the z terms. So it's x squared plus 3x plus y squared plus z squared minus 4z is equal to minus 1. And then I'm going to complete the square. I have 3x. I want to half that to get 3 over 2. And then I want to square it to get my b squared. 3 divided by 2 is 3 over 2. Square it, we get 9 over 4. I'm going to add on 9 over 4, and then I'm going to subtract 9 over 4. So I haven't changed the equation. I've added and subtracted the same number. For y squared, we don't need to do anything. We can leave that as it is. Looking at z now, I've got minus 4z. I want to do minus 4 divided by 2 to get minus 2, and then I want to square it to get 4. And then I'm going to do plus 4 and minus 4. Again, the equation hasn't changed because I've added on and then subtracted the same number. Now I'm doing this so that I can use the equation at the top. The first bracket is x plus 3 over 2 squared. And this third term, z squared minus 4z plus 4, is the same as z minus 2 squared. Now I can read off the answer, because now my equation is in the standard form. Instead of x minus x0, I have x plus 3 over 2. That tells me that x0 is minus 3 over 2. Instead of y minus y0, I just have y. That tells me y0 is 0. And instead of z minus z0, I've got z minus 2. So z0 must be 2. And equal to a squared, I've got equal to 21 over 4. The center must be at minus 3 over 2, 0, 2. And the radius must be the square root of 21 over 4. That's the square root of 3, square root of 7, divided by 2. Let's do another one. Find the center and the radius of the sphere x squared plus y squared plus z squared plus 6x minus 6y plus 6z is equal to 7. And here's the calculation. First, I want to group all of the x terms together, all of the y terms together, and all of the z terms together. And then I want to add on and subtract something so that I can complete the square. So what am I going to add on? I'm going to take the 6. I'm going to do 6 divided by 2. And then I'm going to square it. Always divide by 2 and then square it. Again, there's a typo here. This should be another x in just here. So 6 divided by 2 is 3, and then 3 squared is 9. So I'm doing plus 9 and then minus 9. And then for y, it's the same. Plus 9, minus 9, and also for z, plus 9, minus 9. Rearrange that so that all of the spare numbers are over on the right-hand side. X squared plus 6x plus 9. That's the same as x plus 3 squared. Plus y squared minus 6y plus 9. That's the same as y minus 3 squared. Plus z squared plus 6z plus 9, that's the same as z plus 3 squared, is equal to 7 plus 9, that's 16. Now we have our equation, the standard form. It looks like the equation in the yellow box at the top. So now we can read off that the center is at minus 3, plus 3, minus 3, and the radius is 4. One final example. Here are some geometric interpretations of some inequalities and equations involving spheres. A, first of all, x squared plus y squared plus z squared is less than 4. Well, if we had equal to 4, we would have a sphere centered at the origin. Less than 4 means the distance from our point to the origin is less than 4. So it's less than the radius of the sphere. So we've got the inside of the sphere of radius 2. X squared plus y squared plus z squared less than or equal to 4. That's the sphere of radius 2, like the equals, and everything which is inside that sphere. If we had greater than 4, we would have the exterior of the sphere. So it would be all of three-dimensional space apart from the sphere and the inside of the sphere. And then D, x squared plus y squared plus z squared equal to 4, but with the extra condition that z is less than or equal to 0. That's the bottom half of the sphere, the lower hemisphere. And that is the end of this week's lesson. Next week, I'm going to talk about vectors, the dot product of two vectors, and the cross product of two vectors. Are there any questions?